I thank you all for being present today. Of course, the presenters, the technical support, and the only one attendee for now, but it is still early for many people in the world, so it's really not a problem. So the session today, number 103, is titled Nuclear Cost Economics, and I'm really happy to be able to preside this concurrent session. We will have 4 presenters. The first presentation will be made by Mr. Björn Steigerwald from the Technische Universität Berlin. And he will talk about production cost, uncertainties, and of SMR concept, a model-based Monte Carlo analysis. The second speaker will be Mario Kendziorski, also from Technische Universität Berlin. And its paper is The Economics of Nuclear Power Plant Lifetime Extension, a conceptual approach and lesson from electricity sector modeling in the US, France, and Germany. The last speaker that is still not here is Magdalena Clemon from the Hong Kong University of Science and Technology. And her paper is titled Sources of Cost Overruns in Nuclear Power Plant Construction. And finally, the last presentation will be done by myself, Arthur Lynch, from Centrale Supélec and the CEA in France. And the paper is titled The Stake of Nuclear Planning Optimization in Electric System with Renewable Energy. So due to the fact that we do not have a lot of time, I will ask you to respect the time allotted to each presentation, so 20 minutes. Then we will have 5 minutes of presentation of question from the audience or the other presenters. And in order to start the concurrent session, I will let the floor to Mr. Björn Steigerwald. Mr. Björn Steigerwald, the floor is yours.
Thanks a lot, Arthur. So let me share my screen up. Oops, there we have it. So actually, we are talking about SMR concepts and uncertainties there in production. We will start with an introduction there. We will come to current estimation technique in literature. We will try to evaluate those estimation technique with current manufacturer costs, and then we try to find an investment decision to find a measurement there to measure a possible investment. Is it will it deliver a possible measurement, or is it not a competitive good measurement there to invest into SMRs? So recently there is a big surge of SMR research in literature. So everybody is speaking about SMR concepts. SMR concepts, yeah, that's nothing new. That's our low capacity nuclear power plants. They're existing since 1950. There was a renaming 2010 by Minister Stephen Chu in an attempt to get it work. Traditionally, the IAEA speaks about small and medium-sized reactors. We are speaking about SMR concepts because they're not small and they're not medium-sized. They might have a low capacity below 300 megawatt or below or till 1000 megawatt thermal. So there are a couple of systems on the market which got developed about the last 50 years or longer. Even we have land-based SMR concepts, we have marine-based SMR concepts, we have high-temperature gas-cooled SMR concepts, we have fast neutron spectrum reactors, or in other words, breeder reactors, which got developed at the moment. We have molten salt concepts, we have microreactors with a lot of interest of the military there. So we worked there in the past to write there a big work there and collected a lot of data. So on the right side, you will find actual cost data, manufacturer advertised in the internet at the moment. Going further, we have data there. What can we do with the data? You would like to estimate cost of SMR. SMR costs you can SMR costs have somehow a ratio with big nuclear power plants. So you can write it like costs of large nuclear power plants or nuclear power plants with high capacity divided by costs of low capacity nuclear power plants. That's the same like power plants with that's the same than the power with from the high capacity reactor divided by the low capacity reactor. Going further, we found two literature streams there. One was described by Roswell. That's equation one. We found a second. It was described by Rulston, Lloyd, and others in 2020. That's the second one. With having both equations, the question was there: how is the structure? Is the structure the same? With some elementary computation, you will find out it's nearly the same structure. It ends with a discussion there on the scaling. So the exponent there, the better, or here is the alpha. That's called a scaling factor. If you will estimate costs there, you're coming from a big reactor or from a normal nuclear power plant. So you have somehow to scale the nuclear power plant down to your low capacity reactor. So the discussion will end up there at the scaling factor. The scaling factor at the first equation can be negative. That's a big difference. That's the blue line there. The negativity there, that's a big thing, because normally it's only described for 0.2 till 0.75 by the OECD NEA, and there is no much literature there. So that's a big gap in recent discussion there. I told you the both equations. So we are trying to evaluate that graphically. That's our goal. So we assume a landing rate, a best case landing rate from 10%. We are putting the D there to 1 to equalize it. We assume a scaling factor from 0.1 to 0.85 as a maximum. And we are using those references. We're ending up at this picture. What is this picture telling us? This picture tells us that current manufacturer costs are underestimate in comparison with current theory of cost estimation. Somehow the theory from in respect to the equation named from Rulston will fit best for the PVRs and BVRs. The theory from Roswell 2016 described there first time will fit best for the high temperature reactors. So now we have some theory, and going further, we would like to measure to promote an investment decision. So we have two possibilities. The one thing is the net present value we can calculate. The other thing is the LCOE. That are our assumptions for the LCOE calculation. We have uncertainties there. We have uncertainties in our model there for the investment costs. We assumed there a unified distribution of investment costs. We used a WACC from 0.04 to 0.1, so 10%. We used the load factor from 0.75 to 0.85. And we used the wholesale electricity price from the last year, especially from 2020. So if you calculate that to the first equation, the Rulston, because we neglect the other equation, you will end up at that box plot. So what are you seeing on this box plot? You have a lot of deep negative net present values. You will find there the PWRs with a monotonic form. The highest capacity SMR concept will have the most negative NPV. The lowest capacity SMR will have the lowest NPV. If you're looking to the other groups, we found out that the high temperature and the sodium fast reactor will be a little bit unmonotone, I can call it at that point. So they have exactly the other direction. The lowest capacity will have the less negative NPV there. So negative NPV. We're going further. We receive in our computation. That's not the NPV. That's actually the LCOE. Sorry, the LCOE. So that's wrong there. The LCOE. That's the advertisement at the moment from manufacturers that they call it's around $40 US per megawatt hour. It will be higher at that point because we calculated it in the best case with 2 years construction time. So it will be even more even higher from the costs there. So that's our findings. I told you already. For the LCOE, SMR concepts with high capacity will deliver probably the lowest LCOE you will find because you're running in direction of economies of scale if you have a lot of megawatt, but not on the SMR concept there. So we also had our data set for the manufacturing costs. The manufacturing costs advertised by the manufacturers, showing this box plot for the NPV, nearly the same picture for the PVRs. You will have a monotone form with a little bit of exception for 4, 5, and 6. That's our NuScale, ReSim, and ACPR. And the other will be also a little bit on the other way. Again, the LCOE computation there. Then we ask ourselves about the sensitivity of the NPV and the Monte Carlo simulation on this point. So we have done a sensitivity analysis there. So we increased the WACC, the construction time at the beginning of 10 years. So you will find a 10-year increase of construction time will deliver a 5% higher NPV at first, or not higher, more negative NPV on this point. On the right side, you will see the WACC increase will deliver nearly a quite small influence to the NPV. Going further, we also try to evaluate the sensitivity of the fuel costs and the O&M costs because they are quite uncertain at the moment. Because nobody has a concept online and the fuel is not quite clear. So on the fuel cost increase by 50%, the NPV reacted below 10%. So that effect will be almost only stochastic. On the right side, the O&M will only deliver also again stochastic effects there on this point. So our results there, it's not new. It's there since 1950. Production economics are not favorable to SMRs because we only have 3 concepts online, and those 3 concepts exploded in fact of the costs there, and there's no fabrication already online there. So we received a negative NPV. We received even higher LCOEs than advertised, which should be so. So at the end, since we have this received a net present value which is deeply negative, there's no competitiveness of an investment into SMRs, we can conclude. So thanks a lot.
Thanks a lot, Björn. Nice presentation. I will ask, first of all, if the audience has some question. You can either ask question by using the chat or by raising your hand. It is really no problem. Do the other presenters have some question? Unfortunately, does not seem to be the case. So I have some question. You in your paper and your presentation you just showed us, you present several cost estimation method, and I will ask yourself, what do you think is the most appropriate cost estimation method that you present to determine what is the cost of SMR project?
To determine or to estimate costs there, at the moment we think that the theory in respect to the paper of Rulston 2020 might deliver the easiest way to estimate costs. The big problem there, you not know which kind of scale factor you has to choose there, because those scaling factors, that's the uncertainty. You don't know what they have done there to shrink the reactor to that low capacity reactor size of an SMR concept. So yeah, that might be the best thing.
Okay, so but I also see that in your presentation you say that scaling theory is highly hypothetical.
Yes.
And how does that affect your result regarding cost and NPV?
Actually, we assumed a scaling interval around that knowledge from scaling about 0.2 and 0.75 from the OECD NEA. So our results should be a bit better than already on the market, and actually there is a gap, and you have to work more with more uncertainty and with more knowledge there to receive better results there. So we might be quite close.
So we have a new question from the chat from Miss Loisel. So Apex Spot does not remunerate any new technologies. Difficult to base the mixed design on. What other contract design? Yes. Did you understand the question, Björn?
Not really at the moment. Yeah, that's no new technology, but at the end you don't know for the scaling what have they done there in detail to get to if you're looking on the PWR reactor, and if you're looking on a SMR concept, you really don't know the differences because it's a concept at the beginning. So that's a big difficulty to discover maybe a little bit that scaling problem. That might be the answer to it.
Can I probably have
yeah, please.
Question? I'm the co-author. Hi, nice to be here. I think Rodika's question refers to the fact that you can't innovate based on incremental prices, and that's definitely correct. There are two things that you could theoretically do in terms of contract design. One is, of course, to give a guaranteed price to these units, but that would be, of course, outside of the wholesale market. And the other would be internal cross subsidies within a company that has both conventional and, on the other hand, SMRs. So the real question here, as is kind of indicated, is one of the longer term innovation financing, which is not addressed in this paper, but which is the next step of our work. So thank you very much for the question.
We also have another question from we also have another question from the audience, and I think it's a remark. It says that in the LCOE formula, yeah, IDCs contain twice. In LCOE,
we will review it. That's all I can say at this point.
Okay.
Thanks a lot.
Okay, and as I looked at your presentation, it seems that the revenues that the SMR gets are only from the IPEX, the wholesale market in Germany in 2020. And the fact is, maybe SMR will be able to be flexible, or to have some capacity payments. So basing the NPV only on these revenues maybe little. What will be, in your opinion, all the revenue that SMR may get, and what will be the threshold for SMR, the threshold revenue for them to be profitable?
There is actually no real flexibility on this point. You will get somehow your SMR plant and your fuel, which you have to decompose at the end. So that's not a small flexible system. That's somehow a big system, and you don't know that cost for the next 100 years you will have there to decompose those costs, and so at the beginning that's a power plant, a nuclear power plant with low capacity. So that's no flexible power plant at the end, and you will be much better to use there a PV or a wind farm. It will be more flexible than a nuclear power plant there on this point. So that was the first part of your question. The second part.
Can I just step in here once again? I think it's a similar question as Rodiger just asked on the market design. If you consider it in the conventional way, of course, you don't have capacity instruments at this point, so you would need to create them, and that is very likely probably to happen, as was discussed in other sessions. The question is whether, as a provider, if you have, once you have invested, of course you would have an interest to provide electricity as much as you can from the existing capacity, and that's the question, whether the revenues from the potential capacity is competitive, because you would have to bid against other options. But that's completely outside of the analysis that we're doing here, which is probably more than in the context of what we will see in other papers on competitive electricity markets. You could also say we haven't talked about balancing revenues neither. My impression is that the idea behind it is to provide base or non-flexible capacity, because if you only do it for an intermittent usage, your capital costs are so high that you would not be able to recover your fixed costs. But that's a very hypothetical discussion at this point, but it's of course interesting.
Okay, thank you. I think, is there any other question from the audience? If not, I think we can thank Björn for. I thank you, Björn, for your presentation, and we can go on with the second presentation from Mario Kendziorski. I'm really sorry again. From Technische Universität Berlin, about the economics of nuclear power plant lifetime extension, conceptual approach and lesson from electric sectors, modeling in the US, France, and Germany.
Thanks a lot. Yeah, my talk will be about the economics of nuclear power plant lifetime extensions. This is a joint work with Christian von Hirschhausen, Robin Sogalla, Björn Steigerwald, and Ben Wealer. And yeah, I will start with an introduction. Then I will talk a bit about the situation in Germany and France as a case study or as an example. Then I will present our approach, which yeah, consists of or the first part is a theoretical framework, and the second part is a application using an optimization model. And yeah, and then I will show some results which are still tentative and preliminary, but yeah, at least I wanted to show some plots from our first model ones, and yeah, in the end I will conclude. So if we talk about nuclear power in the context of the decarbonization process, we have to consider that most nuclear power plants were built in the 70s and 80s. That is especially true for the Western world. And if we take a look at the graph on the top left, which shows the construction starts in the world, yeah, grouped by each year. We see that since the 90s, yeah, the construction starts has dropped significantly, and in the last 2 decades, most of new construction starts are done by China. So there's no, or it's quite unlikely that we will see a new era of nuclear power in the future. And considering that, yeah, the duration it takes, or until these nuclear power plants are able to produce electricity is quite long. Even if we would start now, it would take a long time until they are able to produce electricity. And if we look at the top right graph, which shows our remaining budget to stay within the 1.5 degree target, we see that we need to take action now, actually, and it's quite important that we decarbonize our system the next to 20 years and not in the next 30 to 40 years. So there's an urgent need to start decarbonizing now. And if we think about that all these nuclear power plants were built in the 70s and 80s and were actually planned to stay online for 40 years, or constructed to stay online for 40 years. A lot of these power plants will be at the end of their lifetime in the next decade, or they already reached the end of their lifetime. So there's an upcoming discussion how to proceed with these power plants. Should they be decommissioned, or should their lifetime be extended, which is usually associated with new investments into these technologies, since the security standards have changed or increased. So we could think of 2 worlds. One world where all these power plants will end the commercial use according to the planned lifetime. So this would lead to the graph in the top left, where we see that in the next decade, a lot of reactor will be closed. So all these brown bars indicate gigawatts that will be closed in that case. And on the right side, if these reactors or most of these reactors would get a lifetime extension by 10 years or sometimes even 20 years, it would smooth out the decommissioning of these nuclear reactors. Obviously, this is the word aggregated, so this situation differs between various countries. That's why I will focus in this talk on Germany and France, because they are two interesting cases here. And here's a map with the generation capacities in Europe. Yeah, I think it's from 2018. So some nuclear power plants may not be online anymore. So if we take a look at France, we see that it's dominated by nuclear power. So that is nuclear power here in that map. And if we take a look at Germany, we see that the situation is more diverse. We have some nuclear power plants. We have lignite, especially in the east and in the west, and we have also hard coal and some gas. And so in Europe and also worldwide, France is yeah, or has the most nuclear power plants and the highest generation. And this is probably followed historically by Germany and the UK and in Europe at least. And therefore it's interesting to have a look at these countries. So how's the situation in Germany? I think most of you know that Germany decided to end the commercial use of nuclear power plants yeah, until 2023 after the Fukushima incident in 2011. But most forget that in 2002 there was already legislation to end the commercial use of nuclear power, according to that one brown line here in the middle. So the government introduced a feed-in tariff for the renewables, which led to a strong increase later on of PV and wind, and on the other side planned to end the commercial use of nuclear power. However, in 2010, a new government decided to extend the lifetimes of nuclear power plants, and this would have led to the other brown line with the extension of nuclear power plant nuclear power generation until the 30s. However, in 2011, after Fukushima, the current law is active, and this have led to a closure of I think it was like the 10 or 11 oldest power plants, and the remaining plants at active we see here with the colored bars. What was the result from these closures? So as we can see from 2010 onwards, we actually see just a small increase in emissions. So the solid line here indicates the emissions from the electricity sector, and from there onwards we see a decline until today, actually a quite strong decrease in the past years. And in the bottom with the red bar, we see nuclear power, or the share of, or the generation from nuclear power plants in Germany. And we see that it has been decreasing constantly. And but we see also that the decrease in emissions is mainly caused by the deployment of renewables, because one key argument for the extension of nuclear power plant lifetimes is that this would lead to an increase of fossil generation, which is actually not what we want in order to decarbonize our system. However, yeah, if we take a look at Germany, at least, this is not the case. So if you ramp up renewables at the same time, this leads to even a fossil fuel reduction at the same time. So the key to decarbonize is not to extend the lifetime, or necessarily extend the lifetimes of nuclear power plants, but to increase the share of renewables. So the current state in Germany is that still 68 terawatt hours were produced in 2019 from nuclear power. The average load factor was quite high, with 86%, and 12% of the total generation was covered by came from nuclear power. In comparison, new renewables almost or all, I think in 2020 it was already above 50%. Yeah, were contributed by renewables. If we take a look at France, we see that there are still a lot of reactors operating. They produced almost 400 terawatt hours in 2018. The share with 72 is quite high. And one difference compared to Germany is that the load factor is much lower. So there was a record low in 2016 with 56%, and in 2019 it was 68%. So yeah, I think that is a big issue in France. And this is also due to the fact that the age of the reactor fleet is quite old, so it's 35 years. And if we consider that the planned lifetime of most reactors is 40 years, we also see, or we already see, the issue here. The government is faced with the decision to extend the lifetime or to decommission these power plants. And originally there was the goal to reduce the share of nuclear power to 50% by 2025. However, this goal has been postponed, as there's no plan or clear plan, at least, how to proceed. So the most likely situation right now is that nuclear power plants or the lifetime will be extended, at least for the oldest ones. So our approach here is to first discuss a theoretical framework to calculate the intensive and extensive margin of the increase of or decrease of emission. So I won't talk about a lot about these equations now, because I think we don't have enough time for that, and it's just not nice. However, just a few words about it. So we have the share of the output share of generator theta, or theta is the output share of generator I. E is the emission intensity of generator I, and capital E is the emission intensity of the electricity sector. And we put these variables into an equation. We do various transformations. So we have a baseline scenario, then we have a counterfactual scenario, which is denoted with an apostrophe. And then we have the change between these two scenarios, which is denoted with a I don't know how you call it. I think in French it's a circumflex. I'm not sure. However, if we transform these equations, in the end we come to that equation where the change of total emission is decomposed into three components. So there's the change in generation. So this is or that corresponds with the demand, obviously. So there will be a change in generation in the future because we have an increasing demand for electricity due to sector integration. Then there is a term that describes the intensive margin. So this is basically the change in the emission intensity or the output share of each generator times the emission intensity of each generator, and we have an extensive margin which describes just the change in pure work from newly generators, and then in the second part of our approach, we want to apply scenarios. So we use a optimization model which is based on the AnyMod framework. It's a linear cost minimization model with perfect foresight. It's it does investment and dispatch. A nice feature is a dynamic decommissioning. So the setup is a brownfield setup. So we take today's capacities, infrastructure, which is actually calibrated to 2019 because due to the COVID pandemic, all the values for 2020 are a bit off maybe because the demand is in general a bit lower and so on. From there on, we calculate the investment in dispatch and 5-year steps until 2040, where we want, or we say that we have to be decarbonized until 2040. And this model also includes the electricity sector, but also includes heat and industry, transport and gaseous carriers, and also other carriers such as biomass and so on. And the spatial resolution is Europe in 99 regions. Each market zone is modeled, and trading capacities are based on the TY-NDP. Then here for a first model one, we assume the emission price or the ETS to be 20 in 2020, 40 in 25, and 75 in 2030. So these are parameters which may change in the future, but as a first guess, we just chose these and wanted to see what happens. And here are the preliminary results for Germany. So on the left side, you see the generation with lifetime, so some hypothetical lifetime extensions in Germany. So if we would extend today's capacities for 10 and 15 years respectively, more years. So today's generation is around 63, I guess it was in 2020. And this is roughly the amount we also get with our model here. And if we would extend these power plants, which are now online for 10 and 15 more years, we would get this result. So we see that due to the high emission price, even in 2025, a large share of coal and lignite has been vanished and replaced by natural gas and also renewables. And if we take a look at the right side here, we see the difference in generation without these lifetime extensions. So actually our the status quo in that case here. And we see that the 60 terawatt hours from the nuclear power plants is replaced with natural gas mainly and some PV. However, if we take a look at the right side and take a look at the emissions, we see that the decarbonization process is still active, of course. This would lead to some additional, or this leads to some additional emissions, at least for the parameters now. And if we take a look at France, where we assume that there's no lifetime extension, so all the power plants will be decommissioned after 40 years, which means it is a rapid end of commercial use in France in the next 10 years. And compared to a scenario where we extend the lifetimes by 10 years. So on the left side here also we see a scenario with lifetime extension, which is probably the most likely one, and compared to on the right side to a scenario where all nuclear power plants are phased out.
Mario, you still have 2 minutes.
Yeah, it's my last slide. And yeah, we see that in France the situation is a bit different compared to Germany, because France exports a lot, and these the nuclear generation would be compensated mainly by a reduction of exports and also newly added capacities of PV and wind. So in the case of France, this wouldn't lead to more emissions in total, or just a bit more emissions, because in France there's still a lot of potential for renewables and to reduce the exports. Okay, so my conclusion is that nuclear power plant lifetime extensions are relatively expensive. Renewables are the way to decarbonize the system. But our results should be are still quite tentative. So we're still working on the data, and so these are just preliminary results, and we will work on this in the future and then try to combine our theoretical framework with our applied scenarios. Yeah, thanks. So if you have any questions.
Thank you, Mario. There is already some question from the audience, from Ms. Rodika-Loisel, and she asked how storage is accounting for in your model.
We have all the usual technologies. So we have lithium-ion batteries, pumped hydro storages, hydrogen, or ways to produce hydrogen, to store hydrogen, and to use hydrogen in several sectors. Also, of course, the possibility to re-electrify hydrogen. So I didn't show any values here because it's not it was not really important for our results yet. but yeah, we have a variety of storing possibilities in our model.
Is the LTE for 10 or 20 years?
For France, we assumed just 10 years, at least here in these first calculations. So just to have some numbers. Obviously, you could discuss 20 years for some power plants.
Okay.
So maybe that would be a way to create another scenario. So as a sensitivity analysis, if that would have any impacts.
Yeah, maybe. I have a question for that about your approach to measure what is the reduction impact of each technologies, and for example, nuclear extension. What I understand is that from your methodology, your conclusion is that nuclear extension does not decrease the overall emission of the electric system. But isn't it logic, since nuclear reactors are already built and extending them will not change, not impact negatively the emission?
So if the remaining system would stay static, of course, it is logic. But if you take a look at the whole system that has to be decarbonized in the next 10 to 20 years, there might be some effects that, or at least that is what we saw in Germany, that it's not so it's not that obvious, maybe, because you have also renewables, and one thought may be that if you have higher shares of renewables, you have and a lot of volatility, and usually renewables will be feeded in first in the market, and we also see in France already some issues with the load factor, that there is maybe also some complication here. So if you have a lot of renewables, and so the effect is maybe not that clear. However, as our results also show, this can also lead to higher emissions, of course. So we just wanted to take a look what is actually happening, and if you take a look at the dynamic system that changes rapidly, and this is also why we included not only the electricity sector, but also the other energy sectors, because there may be some interesting effects on technology decisions there, but we're not there yet to analyze that, because we're still developing our model. Yeah.
Okay. Also, one other question, because I don't see any question from the
yeah, sorry. So thank you, Christian. Kind of surprising your results. I mean, the substitution between renewables and baseload is kind of surprising without lots of storage and more grid. So what about the curtailment of renewables? What your numbers show?
I haven't analyzed the curtailment yet, actually. So there will be some curtailment for sure if we come to really high share of renewables. But I guess, yeah.
So it's just an intuition, because in our results we have a lot of curtailments when we have a lot of renewables, and what to do with if we have more than 10% of curtailment out of the generation of renewables. No investor will come, it's a private thing. So it's a private sector. So if you have a lot of curtailments, they won't install the turbine. So yeah, it's just a remark.
I guess the approach that we took here is from a the perspective from a social planner. So we're not analyzing any private firms if they can earn money with these investments. So that would be a different perspective, and it's also interesting. But in that case, we're trying just to optimize the system as a whole, and also I think it highly depends on the scheme. So if you have a feed-in tariff, it still would be worthwhile for private investors to invest into renewables if the cost, or if there's a feed-in tariff, for example.
Yeah, I think in 2040 it will be market only plus a complement as it is today for new plants. So I think in 2050, no feed-in tariff, and for curtailments will be no reward. Now it's just a remark. So let's
yeah, obviously there are different problems, but this is not the aim of the model here, because we take another perspective, and I guess these funding schemes differ also a lot between countries, right? So in France it's different compared to Germany and so on. So it's
but
quite
this is
hard
European
to
directive. This is the directive in the Treaty of the Functioning of the European Union. So no more feed-in tariff in the future. But just a remark: any private has its own tool and is modeling these things. So I think that social planner should be aware of these planning schemes that are run by each investor. Even small ones, they have their own tools to model, and they know what to expect. But I understand your approach is dealing with one thing only. Yeah, thank you.
Can I just add on the storage? I think I mean that this is really optimization. So let's say solar and other capacities are built as long as they contribute to the overall cost minimization over time. And there's a quite, as Mario said, there's a quite complex storage infrastructure behind that is not shown here, and but of course the perspective here is one of unified cost minimization, which is the nature of this model. But I think in terms of the storage, it's probably the most sophisticated that is there, and I think we could for the paper we should specify the nature of the storages between shorter and longer term storages. So thanks for the suggestion.
Yeah, I have one last question. In your result, I did not see any cost estimation. What would be the related cost estimation of non-extension of nuclear power plant?
Yeah. We could do an analysis on this. However, I guess it's quite difficult because we give the model just capacity for free if we extend the lifetime. So we need to associate cost with these lifetime extensions. Yeah, that would be possible. But I guess it's quite hard to get good estimations on how much does it cost to extend the lifetime for all France's power plants, for example, by 10 years. Yeah. So I mean, maybe there are numbers, and that's a good remark.
Yeah,
so maybe that's interesting.
Data. I mean, the data are surrounding the cost of life extension of nuclear power plant at least is well known in France, or at least published. So maybe you can look at the EDF data about the grand carénage, and maybe it will be a good estimation.
That would be interesting to compare it. Yeah, thanks.
So yeah, I don't think I see any other question from the audience, and we should probably move on. Thank you, Mario, for your good presentation. Just to note, we have some news. Miss Magdalena Clement, that was supposed to present sources of cost overruns in nuclear power plant construction, will not be able to join. She does not seem available. So we are skipping a presentation and directly going to the full presentation, which is fortunately my presentation. About the stake of nuclear planning optimization in electric system operation with renewable energy. It is a paper that was written with in collaboration with Yannick Perez, the IAEA chairman from Central Supélec, Sophie Gabriel and Gilles Matonnière. The presentation will be structured as such. First of all, the backgrounds and objective of the paper, then the method and model used to assess the impact of nuclear planning optimization on electric system operation with renewable energies, then the result, and lastly, some concluding remarks and limits, and I hope I will have your question regarding this paper. The general context is quite simple. It is the fact that viable renewable energies are expected to meet most of the future electric demand. And this integration of a larger viable renewable energy will drastically increase the flexibility required to meet the demand-supply equilibrium that is structural to the electric system. And all of that create a new paradigm for nuclear power plants, where the flexibility will be determining the future role. So as mentioned before, and as you probably know, in most countries, and also partially in France, nuclear power plants have been traditionally used as baseload of mean of generation due to their high fixed cost and low variable cost. Due to that fact, the modeling literature typically does not model the flexibility potential of nuclear power plants, as well as their flexibility constraint. And nuclear is often represented either as an inflexible mean of generation or conventional thermal technology such as gas or coal. So our research question behind this paper was to try to determine what are the potential benefits of using nuclear flexibility in renewable-driven electric system. What we found when we looked at the literature was that the literature regarding nuclear flexibility, its physical constraint, and its related cost is really rich. However, it is almost never put in place into electric system modelization. Some papers did implement some flexibility constraint into their modeling practices. It can be ramping ramps, xenon transient, and determine that at least nuclear flexibility can be a good way to integrate viable renewable energy and decrease the electric system cost. However, what we found is that one physical constraint, which is related to maintenance and refueling outages, and does frame nuclear planning seasonality, is not represented in most of the modeling literature. So the objective of the paper is to try to evaluate the impact of refueling and maintenance outages that really define nuclear planning seasonality, and to see its impact on electric system operation with renewable energies. Just a quick overview of what is refueling and maintenance outages. So nuclear reactors, contrary to all the thermal technology, most of them need to stop for refueling and maintenance operation. And what differs from all the thermal technology is that the duration of those outages is really long. And it accounts for approximately 20% of the total lifetime of nuclear reactors. We define in this paper what is an irradiation cycle. It is the period between two refueling or maintenance outages where the nuclear power plant is able to produce electricity. And the duration of this irradiation cycle really depends on the nuclear reactor size, its design, or even the plant manager for strategy. And due to some different constraints, like workforce limits, it is impossible for reactors, for all reactors of a nuclear fleet to stop simultaneously. So one plant manager, when deciding when to stop its plant, need to take into account its own physical constraint, but also the schedule of the fleet in order to have coherent planning. And all of that results in what we call an optimized nuclear availability planning, where nuclear availability is not constant to a year, with higher nuclear availability when the system needs nuclear to balance between demand and supply, and a lower the nuclear availability when the electric system needs it less. And we get the example of France when we can see that the average weekly nuclear availability on the period 2015 and 2019, where we have a higher nuclear availability in winter when there is a high electric demand, and a lower nuclear availability during summer when there is a lower electric demand. So now the method that we build and the model to assess the impact of nuclear planning optimization on electric system operation. The model is structured in 4 steps. First of all, we create what we call an heuristic model that aims to simulate nuclear planning optimization. Then we simulate a simplified electric system operation with the resulting heuristic planning found with our model. What we do after that is that we compare the simulation result of the electric system operation with the heuristic planning and we compare it with the result of another simulation of the same electric system, but with a different nuclear planning assumption, where we consider that nuclear planning is not optimized, meaning that there is a constant nuclear availability. Lastly, we perform a sensitivity analysis and we simulate different capacity cases where there is a different share of variable renewable penetration and nuclear capacity. The first model that we built is our heuristic planning model that aims to simulate nuclear planning optimization. It is a mixed integral linear programming model whose objective function is to maximize the nuclear availability during high demand period. It means that the model schedules maintenance and refueling outages during a low electric demand period when the electric system needs nuclear less to balance between the demand and the supply. Each reactor's behavior is constrained by 3 different sets of constraints. First of all, the irradiation cycle constraint, which frame how long can reactor remain available before they need to stop for an outage. The second set of constraints is linked to maintenance and refueling duration, and how long must reactors remain unavailable before they can start producing again. And the last set of constraints is linked to human resources and utility requirements, and it limits the number of reactors of a fleet that can go offline simultaneously. And we run this model with a standardized nuclear reactors assumption. We based our nuclear standardized reactors on the French fleet. So each reactor is pressurized water reactors with 1 gigawatt electrical power, a cycle length, so irradiation cycle length of 15 months, and an average availability factor of 79.1%, which is the historical nuclear fleet availability factor since the first reactor was built. We get the resulting planning, and we run our model with 3 different fleet size levels. So one with 20 reactors, one with 40 reactors, and one with 60 reactors. And we can get 2 results from this graph. The first one is that our heuristic planning does replicate the dynamics of realistic nuclear planning optimization with a higher nuclear availability during high demand period and a lower nuclear availability during the low demand period. The second result that we can get from this graph is that nuclear planning optimization seems to be of primary importance as the number of reactors in the capacity mix increase. We have a higher difference between high demand period and low demand period in the 60 reactor case than in the 20 reactor case. So once we have our heuristic nuclear planning, what we need to do is to simulate an electric system operation. And we do that using the unit commitment economic dispatch model, that is the anti-risk simulator model from the French TSO RTE. Its objective function is to minimize the operational cost of 1 calendar year at a hourly time step, and it discriminates between technology based on the ascending order of marginal cost, meaning that it replicates the merit order approach of the current European wholesale market. There are, of course, a lot of constraints in this model linked to security of supply or thermal generation, but I will not detail them here. Now that we have our model and our planning, we need to know what kind of system we are modeling. We chose to focus on a simple system, and that was a deliberate choice in order to focus on nuclear planning optimization. We only model one country, France, and we chose this country due to the data availability regarding nuclear and viable renewable energies. We only simulate one weather year, which is 2006. We consider that it is a representative weather year based on the literature. We represent 5 generating technologies: wind onshore, wind offshore, solar PV, nuclear, and gas. Of course, there are a lot of generating technologies that are missing, but we really chose to focus only on few technologies to assess the impact of nuclear planning optimization. The last assumption is that there are no interconnection with neighboring balancing areas. Of course, it is really a limiting factor for the robustness of the result, but those limitations will be discussed later in the limitation part of the presentation. Of course, the model that we simulate, the electric system that we simulate, are some cost and technical capacity assumption. I will not detail them here, but just to remind you that each technology has some related nominal capacity, related cost, related flexibility constraint, and of course some related environmental impact, measuring CO2 equivalent, and derived from the IPCC. So now the sensitive analysis that we are performing. We have 5 different viable renewable penetration scenarios that range from 0% of the total electric demand to 80% of the total electric demand, of course, if no curtailment occurs, and 3 different nuclear fleet size scenarios for so 20 reactors, 40 reactors, and 60 reactors whose nuclear planning we already completed. And the rest of the electric demand is ensured by open cycle gas turbine with a 38% electrical efficiency. So all of that gives us 15 different capacity mix scenarios, where in some cases we have high penetration of viable renewable penetration and high number of nuclear reactors, and in other scenarios we have low viable renewable penetration and low number of reactors. And what we do with those 15 different capacity mix scenarios is to do 2 simulations, one with the heuristic planning that we computed before and that I presented to you, and another simulation with the nuclear planning assumption where nuclear planning is not optimized, meaning that there is a constant nuclear availability. And we compare the result of those 2 simulations in each of our 15 cases, which allowed us to determine what is the impact of nuclear planning optimization for each of our 15 cases. So now the result. The first result that we tried to assess was linked to thermal dispatch and the influence of nuclear planning optimization on the thermal dispatch. And the first result is the fact that in cases with low variable renewable penetration and low number of reactors installed in the capacity mix, nuclear planning optimization does not seem to influence electric system operation with renewable energies. It seems that in cases where nuclear does run as baseload, nuclear planning optimization is not of primary importance on electric system operation. However, what we also found is that in cases with higher variable renewable penetration and a higher number of nuclear reactors installed in the capacity mix, nuclear planning optimization has 2 effects. The first one and the biggest one is the decreasing use of peaking gas plants. It means that there is a decreasing need for peaking plants to balance between the demand and the supply thanks to nuclear planning optimization. The second effect of nuclear planning optimization is the decreasing nuclear production. It seems counterintuitive because if gas production is reducing, it does decrease, nuclear production should increase. But the fact that it decreases is linked to energy curtailment, which are some results that will be detailed a little bit later. The second type of result that we tried to assess was linked to operational cost and CO2 equivalent emission. And what we found is that the impact of nuclear planning optimization on operational cost and CO2 equivalent emission is approximately the same as with thermal dispatch. in cases with low variable renewable penetration and low number of reactors installed in the capacity mix, nuclear planning optimization does not seem to have a great influence on operational costs and CO2 equivalent emission of the system. However, in cases with higher variable renewable penetration and higher number of reactors installed in capacity mix, nuclear planning optimization does decrease quite strongly the operational cost of the system and its CO2 equivalent emission. The third set of results that we had in this paper is linked to energy curtailment. We think that it is one of the most crucial results of the paper, and it is the fact that in cases when variable renewable penetration is equal or higher than 40% of the total electric demand, nuclear planning optimization does decrease the total energy curtailment level of the electric system. Not only does it decrease the total energy curtailment level of the system, but also each technology curtailment level. It means that nuclear planning optimization does decrease solar curtailment, wind curtailment, but also nuclear curtailment that may occur when nuclear is not flexible enough to adapt to the electric demand variation. This is really a structural result of our paper, the fact that nuclear planning optimization in cases with high variable renewable penetration does help variable renewable energies integration in the electric system. The last set of concerns that we tried to determine was the impact of nuclear planning optimization on market prices and technology revenues. And what we found is that this effect is ambiguous. In some of our 15 cases, we found that market prices were increasing, in some other it was decreasing, with no particular trend. So we tried to look at the result a little bit more closely. And what we found is that nuclear planning optimization does decrease the occurrence of negative prices in all of our cases. So it should have an increasing effect on market price. However, in some of our 15 cases, the increasing effect of nuclear planning optimization on market price were offset by a decreasing occurrence of peaking price, which was lowering the overall market price level. If we illustrate that with the 40% variable renewable penetration and 60 reactor case, we find that the total number of hours where the price is negative does indeed decrease by 30%. But due to the fact that the number of hours where the price is higher than $50 per megawatt hour also decreased by 24%, the overall effect on the average market price per megawatt hour is that it decreases. If we look at technology revenue, we have the same result. In some of our 15 cases, technology revenues were increasing, and in some other it was decreasing. When we looked at the output share and at which price each technology output share was sold, we found that there was a depleting occurrence of peaking of the output share of technology sold at negative price, but the benefit may be offset by decreasing output share sold at peaking price. And if we illustrate that also with the 40% variable renewable penetration and 60 reactor case, we see that for all technologies, the revenue does decrease mainly due to decreasing output share sold at peaking price. So if we try to have some conclusion on the result, what are the main results of the paper? The first main result, and I think this is really important to remind that, is that nuclear planning optimization has negligible impact on electric system operation in cases with low variable renewable penetration and low nuclear capacity. This corresponds to cases where nuclear run as baseload and nuclear flexibility is not needed. The second result is the fact that in cases with higher variable renewable penetration and higher number of nuclear reactors installed in the capacity mix, so cases where nuclear does run flexibly, nuclear planning optimization has three effects. First of all, it decreases the electric system operational cost and CO2 equivalent emissions. Secondly, it does facilitate variable renewable integration in the electric system due to a decreasing level of energy curtailment. And lastly, it decreases the occurrence of negative market price, but the overall impact of market prices and technology revenue is then determined due to a decreasing occurrence of peaking market price. What we can get is that nuclear planning optimization seems to be of primary importance when the flexibility required to nuclear power plant does increase. Of course, there are some limitations to our work. We listed a few limitations. The first one is that the model that we use to assess the impact of nuclear planning optimization on electric system operation is a simplistic model with few generating technology, only one country represented as one node, and only one weather year. So it limits the robustness of the result, and the result should be extrapolated with care. The second limitation is the fact that we do not represent some flexibility levels. We do not have storage capacity. We do not have demand side response. We do not have interconnection with neighboring balancing areas. And the integration of those flexibility level in a system that is a little bit more complicated will likely lessen the benefit of nuclear planning optimization found in this paper. The last limitation that we wanted to highlight is the fact that the nuclear planning optimization model that we built is a heuristic one. It does not totally replicate reality. For example, we use standardized reactors, which is not the case in most nuclear fleet in the world, with different reactor size or different reactor design. And there are also no uncertainties on outages duration, which is often the case in nuclear operation, where when some outages duration may be longer than planned. So I hope I was clear enough and not too long. I will be happy to answer to all of your questions and have your remarks. Thank you. So is there some question from the audience? Yes.
I would have two questions, if I may. Thank you very much. I would have one on the nature of the modeling. You have this mixed integer LP, and then you have the dispatch modeling. So do I see correctly that it does not take into account investment decisions or capital decisions, but it's kind of operational, and you take the capacities exogenous? And because otherwise, I think the two elements would need to be combined, which would make it much more complicated. And then, if you could re-show the slide on the changes of prices, I think it was in the late 10s, because I did not understand there seem to be two effects, one on decreasing prices, but also one on changing the energy mix between gas and this one between gas and nuclear power. So one on the model and then one on the price effects. Thank you very much.
Yeah, thank you for the question. You're totally right. The economic dispatch model that we use is not a capacity expansion model. We do not optimize capacity in our cases. The only capacity that is not fixed exogenously is a gas capacity that is just necessary to ensure that there is no loss of load. We chose to do that due to the fact that we needed to build a model that aimed to replicate nuclear planning optimization. And the problem with that, when one tried to use a capacity expansion model, is that it is really difficult to integrate the nuclear schedule dynamics in a capacity expansion model. So what we try to do is to have an incremental approach. First of all, to build nuclear, to have some exogenous nuclear fleet, to build a nuclear schedule for this fleet, and integrate this nuclear schedule in a simulation model that will allow us to assess the impact of nuclear planning optimization. Of course, building a model that would integrate both capacity expansion that will allow us to have some investment decision would be really beneficial for the result. But just to have just a simple example, imagine that in the model you have all 10 reactors with a certain nuclear planning, and the model must decide whether it wants to invest in a new nuclear planning, in a new nuclear plant. Then the nuclear planning should change because there are no longer 10 reactors, but 11 reactors. And so the computational cost of this kind of capacity expansion model would be really heavier, and it does not still exist. So of course, yes, it will really be incredible, really good added value, but in terms of computational costs, may be really difficult to put in place. The second question that you ask about, prices and the effect and the price evolution, and you're right to have made the link with the use of gas. The fact that the number of negative price of hours where the price is negative does decrease is directly linked to the decreasing energy curtailment level. Similarly, the decreasing number of peaking price in the electric system simulation is linked to the decreasing use of peaking gas plants that are the marginal technology that explain peaking prices. So prices tend to be less volatile and center themselves around the marginal cost of nuclear in this model, at least. I hope that answers your question.
Can you just go one to the next slide? Yeah. Or if there are other questions, go ahead. I was just wondering about the degree of flexibility. How is it defined? Is it in ramping per minutes, or what is the degree of flexibility that you have? And then I'm sure that this translates into the prices and into the capacities as well.
So you're asking about the flexibility constraint of the model.
Yeah.
So the flexibility constraints are a little bit more detailed in the paper, and of course not here. The first flexibility constraint we tried to assess was ramping constraint. We wanted to know what kind of ramping constraints were realistic, and what we found is that in most of the modeling literature, ramping constraints are mostly at 25% per hour, at least for nuclear. But we also found that this is a way of representing the historical use of nuclear power plant. And by looking at the literature surrounding physical constraint, for example, the International Agency of Atomic Energy, and the OECD NEA literature, we found that ramping constraint does not seem to influence nuclear reactors' behavior at an hourly time step, but only at the minute time step. For example, the ramping constraint of nuclear power plants are 2% of the nominal power per minute, meaning that at the hourly time step does not influence nuclear flexibility. So the flexibility, we limited our flexibility constraint in this paper to minimal power. So the minimum power where nuclear can operate, and of course the nuclear schedule that frame a nuclear flexibility.
Okay, thank you.
Is there some other question from the panel?
Yes, I have a question regarding the possibility to have negative prices in your results. So I guess it is linked to the interest model. Can you explain quickly how it is represented?
Yeah, so the negative price in our model do happen when there is a energy curtailment or spilled energy from the system. And we the question of having representing the price and how much must it cost to have some negative price was really critical. So what we chose was to look at the historical data for France at least, and have the mean negative price in France when it appeared on the day-ahead market. And that was our choice. Of course, it is limiting, and that's why what we want to show in our result is not really the numerical results are really case specific. But what is interesting to look at is the fact that the number of hours the price is negative does decrease, not that the average market price decrease. That's why we say that the effect on market price and technology revenue is ambiguous.
Okay, thank you. That's interesting to see how you manage this.
So no new question from the audience. Okay, is there generally speaking, is there any question for the other presenter? Maybe someone didn't dare to ask question before, I don't know. Okay, it does not seem to be the case. So I think we will be able to end this session. First of all, I would like to thank Clémence for doing the technical support, and thanking all presenters and attendees for being there and participating in this concurrent session about nuclear cost economics. I would like to remind the presenters to upload their presentation on their dashboard for all participants of the IAEE conference to look at. And on those thanks, I would like to close the session. Thank you.
Thanks a lot, and to all the speakers, it was really interesting. Bye.